Hi, my name is Julian Hall, and this is a talk about high-performance computational techniques for the Simplex method. I'll begin with a swift revision of LP theory and the Simplex algorithms, with the aim of introducing my terminology and notation for standard theory. Then I'll look at a few advanced algorithmic and computational techniques for serial Simplex implementations. Finally, I'll present parallel techniques for both structured and general problems. Linear programming is the fundamental model in optimal decision making. There are two main solution techniques and both have their places. Large problems can have very different numbers of variables and inequality constraints. Computationally, it's essential to exploit sparsity in the constraint matrix A, and it may be valuable to exploit any inherent structure. The matrix for this toy problem stare, where each pixel corresponds to a non-zero value, illustrates both. The set of feasible solutions of an LP forms a convex multidimensional polyhedron. A vertex of the feasible region is partitioned into m basic components and n minus m non-basic components. The equations and variables are partitioned correspondingly, allowing the basic variables to be expressed in terms of the non-basic variables. The reduced objective function, obtained by eliminating the basic variables, is given by the objective value at the vertex, f hat, and the reduced costs, cn hat. At the vertex, when the non-basic variables are zero, the partition is optimal if there is both primal feasibility and dual feasibility. The dual problem has the same data as the original primal problem, and the two problems are related in valuable and interesting ways. Partitioning the equations S and C yields solutions in terms of the basic dual slacks, and a reduced objective in terms of the reduced right-hand side vector B hat. At the vertex, when the basic dual slacks are zero, the partition is optimal if there is both primal feasibility and dual feasibility. The dual simplex algorithm for an LP is the primal algorithm applied to the dual problem. The structure of the dual equations allows the dual simplex algorithm to be applied using the familiar primal simplex tableau. The primal simplex algorithm assumes primal feasibility and seeks dual feasibility. In tableau form, the reduced costs are scanned for an index Q to remove from the non-basic set. A ratio test between entries in the pivotal column and the reduced right-hand side then determines the index P to remove from the basic set. The indices are then exchanged between the two sets. The elegance of the primal-dual relation continues with the dual simplex algorithm. It assumes dual feasibility and seeks primal feasibility, and can be viewed as the transpose of the primal algorithm. First, it scans the primal infeasibilities for an index P to remove from the basic set. Then it performs a ratio test between entries in the pivotal row and the reduced costs, to determine the index Q to remove from the non-basic set. The indices are then exchanged between the two sets. The pivotal row and column are used to update the reduced cost and reduced right-hand side according to the steps made in the primal and dual spaces. Thus, each iteration and implementation requires the pivotal row and the pivotal column. The algorithm only works because the objective improves by a non-negative amount. The primal simplex algorithm is the traditional variant, but has the disadvantage that when the primal LP is tightened, the solution is not primal feasible. This happens, for example, after branching on a variable or adding a cut when solving MIPs. The dual simplex algorithm is the preferred variant. It's easier to get a dual feasible point. It allows more progress to be made in many iterations, as we'll see later, and the solution is dual feasible when the primal LP is tightened. The standard simplex method ensures that all possible pivotal rows and columns are always available, but at a catastrophic computational cost. The revised simplex method computes the pivotal row and column as required by solving systems of equations with B or B transpose as coefficients, Ftran and Btran. This requires an invertible representation of B. The pivotal row is then formed via a matrix vector product with the sparse matrix N. Representing the inverse of the basis matrix requires a factorization technique to obtain an LU decomposition with, ideally, no more non-zero entries than the original matrix. The prohibitive cost of factorizing every basis matrix is avoided by exploiting the relationship between successive basis matrices. There are a few general approaches and many variants. The simplest is the original product form update, as derived, but other, more complicated schemes are more efficient in terms of sparsity and have better numerical stability. Eventually, it is more efficient computationally, or necessary for numerical reasons, to re-invert rather than continue to update. To illustrate the value of most of the techniques in this talk, I'll use the standard industry test set of 40 LP problems compiled by Hans Mittelmann. They have a wide range of dimensions with some extreme profiles, ratios of numbers of rows to columns, and density, either as a percentage of non-zeros or average number of non-zeros in the dominant dimension. The Mittelmann solution time measure for a particular solver or algorithmic variant is obtained by shifting all times up by 10 seconds, computing the geometric mean of the logs of these shifted times, and shifting the exponent of this geometric mean down by 10 seconds. The bound flipping ratio test is one of the major reasons why the dual simplex method is preferred. It's only relevant when solving general bounded LP problems, but these are widespread, notably when solving relaxations of integer programming problems, when the relaxed binary variables have lower and upper bounds of 0 and 1. One-sided and free variables are still accommodated by one or both of the bounds being infinite. At a vertex, non-basic variables are not generally 0 now, as they lie at either their lower or upper bound. Partitioning the equations as before yields an expression for the basic variables in terms of their values at the vertex, and change delta n in the non-basic variables. When delta n is 0, the optimality conditions are primal in feasibility and a sign condition on each reduced cost, according to whether the corresponding non-basic variable lies at its lower or upper bound. Forming the dual of the general bounded LP and eliminating the basic variables is a tedious process and yields the reduced objective. If one basic primal variable lies below its lower bound, then the dual objective can be increased by increasing the corresponding basic dual variable from 0. As the dual objective increases, some non-basic dual variable, Sj, is zeroed. If the corresponding non-basic primal variable flips bound, then hat BP increases. If it is still below its lower bound, then Sj can be allowed to change sign and the dual objective improves by increasing Sp further. In general, the gradient in the piecewise linear dual objective function changes at a set of breakpoints. These are easily computed and, once ordered, can be analyzed to identify when the dual objective is maximized. This allows progress that would otherwise require multiple iterations to be achieved for the computational cost of a single simplex iteration. Exploiting hyper-sparsity in the revised simplex method has yielded a major improvement in performance for amenable LP problems. The major computational components in each iteration are two system solves and a matrix vector product. The right-hand side vectors of the linear systems are sparse, being a column of the identity matrix and a column from the constraint matrix. However, because the inverse of the basis matrix may be sparse, the solutions of these systems may be sparse. This is because they, and the result of the matrix vector product, are the combination of a small number of rows or columns of a sparse matrix. Hypersparsity is remarkable because the inverse of a sparse matrix is generally dense. Indeed, the inverse of a random sparse matrix is usually full. For the LP test problem STAIR, the optimal basis matrix is sparse, but its inverse is more than half dense. Hence, the solution of Bx equals B is dense, whatever the right-hand side. For the test problem PDS2, the optimal basis matrix has a density of 0.07%. However, the structure of the matrix is such that its inverse has a density of 0.5%. Hence, when the right-hand side of Bx equals B is sparse, the solution is sparse, since it is a combination of only a few columns of the inverse. To illustrate the phenomenon of hypersparsity and demonstrate how it can be exploited, consider the triangular solve Lx equals B that is performed by forward substitution. Forward substitution loops over the rows, taking a component Rj of the solution from the right-hand side, since the diagonal entries of L are all 1, and then substituting its value into the remaining components of the right-hand side by adding in Rj times column j of L. However, whatever the matrix L, when the right-hand side is sparse, this is initially inefficient, since most components Rj are 0. However, this inefficiency disappears as the right-hand side fills in. Efficiency is improved by testing whether Rj is 0, so avoiding multiplications and additions with 0. When the solution of the system is sparse, very few values of Rj are 0. The computational cost, indeed, is dominated by the test for 0. Graph traversal techniques are used to identify the set of indices of the non-zero values of Rj efficiently. How can hypersparsity be exploited in the other computational components? BTran requires transposed triangular solves. These can be performed by backward substitution, in which each component of the solution is formed using an inner product between a row of the upper triangular matrix and the components known to date. When the solution is sparse, most of these inner products are 0, because the intersection of the sparsity patterns of the solution and matrix row is empty. But this cannot be identified efficiently. However, by also storing the triangular matrices row-wise, BTran can be performed efficiently in the same way as FTran. Price is the product of a sparse row vector and a sparse matrix. If the result is sparse and formed via a sequence of inner products, most of these will be 0. The result is formed efficiently by storing n row-wise and combining the rows corresponding to the non-zeros in the vector. Exploiting hypersparsity in all components of the simplex method allows amenable LP problems to be solved in a time proportional to their dimension rather than as much as its square. The effectiveness of exploiting hypersparsity is demonstrated using the High's dual simplex solver and the Mittelmann test set, with a time limit of 100,000 seconds. When exploiting hypersparsity, 37 of the 40 LPs are solved. When not exploiting hypersparsity, only 34 are solved. Unsurprisingly, the iteration count is largely unaffected on average, although there is some variance due to the effect of numerical rounding on tie-breaking. On average, the solution time increases by a factor of only 2.3, but by more than 10 for 4 problems. This is generally due to the decrease in iteration speed. Overall, the relative solution time measure is 2.57. The effect of exploiting hyper-sparsity is greater in larger and easier problems than are represented in the test set. Cost perturbation in the dual simplex method is important for both algorithmic and computational reasons. If some of the non-basic dual values are 0, then the vertex is dual degenerate. This occurs frequently in practical problems. It means that an iteration of the dual simplex algorithm may not lead to a strict increase in the dual objective. Since this is the only reason that the simplex algorithm terminates, it may stall at a degenerate vertex for many iterations, or never leave, cycling indefinitely. Cost perturbation adds a small random value to some or all of the cost coefficients, leading to non-basic dual values taking, at worst, small positive values. This ensures that an iteration of the dual simplex algorithm yields at least a small positive increase in the dual objective. When an optimal solution is obtained, the perturbations are removed and the dual values are recomputed. It may be necessary to perform simplex iterations to regain optimality. With cost perturbation, HIGHS solves 37 of the 40 test problems. Without, it solves only 27 in the time available. For the problems that are solved, the iteration count increases by 36% on average, but by considerably more for some problems, and, presumably, even more for some of the problems that aren't solved. The increase in the solution time is even greater, because there is a decrease in the iteration speed that is significant for some problems. This is because cost perturbation increases the extent of any hypersparsity. Overall, the relative solution time measure is 3.8, reflecting the many problems not solved. Between the late 1980s and 2010, many people tried to exploit parallelism in the revised simplex method, since the value of doing so is very high. However, success on general large-scale sparse LP problems was very limited. Since then, I have been involved with 2 projects that have obtained significant performance improvement when solving structured LP problems, and performance improvement for general problems that has translated to at least one commercial solver. 2-stage stochastic LPs have column-linked block-angular structure. One set of variables correspond to first-stage decisions, and the other variables are grouped into sets corresponding to second-stage scenarios that will occur with a particular probability. The objective is then the expected cost. In stochastic MIP problems, some or all of the decisions are discrete. This study of stochastic MIPs came from a power systems optimization project at Argonne, with stochasticity coming from wind generation. The MIP was to be solved via branch and bound, with the root node solved using a parallel interior point solver, PIPS. Subsequent nodes were to be solved using a parallel dual simplex solver, PIPS-S. It is convenient to permute the first stage variables and constraints to the end of the LP. The key to efficiency of a simplex implementation is the inversion of the basis matrix. It inherits the structure of the LP, with rectangular diagonal blocks corresponding to the basic variables in each scenario, and a set of columns corresponding to the basic first stage decisions. Non-singularity of the basis matrix means that the diagonal blocks are tall with full column rank. The scope for parallelism is immediate. Subdiagonal entries of a block can be eliminated independently of other blocks. These elimination operations are applied independently to blocks of the first stage columns. Rows that have not yet been pivoted on are accumulated and elimination is completed. Parallel Gaussian elimination yields a block LU decomposition of B. This, in turn, yields scope for parallelism when using the decomposition to solve systems of equations. There is also scope for data parallelism in price, since the matrix N inherits the structure of the constraint matrix. The code was implemented in C++ by Miles Lubin, using MPI to communicate between processors. It's a dual simplex solver based on numerical linear algebra routines used in the open-source simplex solver CLP. Data are distributed over processors, allowing parallelism to be exploited over processors for individual computational components. Tests were carried out on 2 stochastic LPs from the literature, as well as 12 and 24-hour unit commitment problems from the Argonne project. Relative to CLP, there was a serial performance hit due to the lack of some algorithmic features, and the numerical linear algebra being less efficient with respect to sparsity. However, on 32 cores, the near-linear speedup meant that pips S had more than caught up in most cases. For larger instances, and using 256 cores, pips S was tens or hundreds of times faster than CLP. Miles had access to the Blue Gene supercomputer, so set up a larger 12-hour unit commitment instance. Clever crash starting meant that a problem with 500 million variables and constraints required only tens of thousands of iterations to solve, and, as the numbers of cores were doubled, the iteration speed continued to increase. The holy grail of parallel simplex is meaningful performance improvement for general, large-scale sparse LP problems, and I've been striving towards this on and off for almost 30 years. A byproduct of this is the open-source linear optimization software, HYSE. HYSE was originally written by Chi Huang Fu to study parallel simplex for general LP problems. Written in C++, it has a dual simplex solver with standard algorithmic enhancements and efficient numerical linear algebra. In addition, HYSE has 2 parallel variants. SIP exploits the limited task and data parallelism in standard dual revised simplex iterations. pami exploits greater task and data parallelism via minor iterations of the dual standard simplex method. The full sequence of computational components of the dual revised simplex method is easily written with data dependencies that appear sequential. The aim of SIP was to exploit slack in these data dependencies. One expensive ftran operation can be overlapped with choosing the pivotal column and the subsequent cheaper ftrans. The only data parallelism lies within price and one pass when choosing a column. Although partitioning these components column-wise looks embarrassingly parallel, on modern shared memory systems, the operations are memory-bound, limiting the speedup to the number of memory channels. Finally, overlap the cheaper ftran operations, which themselves can be performed independently. There is only scope for 4 threads, unless the number of columns is very much larger than the number of rows, so that price dominates. The parallel multiple iterations of pami offer greater scope for exploiting parallelism. The technique of forming a small number of tableau rows to perform minor iterations of the standard dual simplex method isn't new, and is analogous to multiple pricing for primal simplex. In preparation for minor iterations, there is a task parallel set of btrans. Each minor iteration has a data parallel price and then data parallel choose C. After the set of minor iterations, There are then multiple task parallel F-trans to accommodate the basis changes. To judge performance, first look at the serial overhead of using minor iterations. PAMI fails to solve 3 of the problems previously solved. This is the first time it's been tested on these problems. Although it's faster for a few problems, it's a lot slower for some and, on average, it's 60% slower. Incorporating the penalty for the failures, the Mittelmann measure makes serial PAMI worse by a factor of just over 2. Running with 8 threads, PAMI performs an identical sequence of iterations, so the speed-up is only a consequence of iteration speed. This is better by a factor that is at least 1.15, is 1.9 on average, and 2.4 at best. The extent to which the parallel performance of PAMI makes up for its serial overhead is seen here. For some problems, it is slower than the serial dual simplex solver, but on average it is faster by a factor of 1.16. For one problem, a combination of decreased iteration count with increased iteration speed means that it is solved more than 6 times faster. Overall, the penalty for the failures means that the Mittelmann measure is worse for PAMI than it is for the serial dual simplex solver. This is a research code. There is significant scope for improvement. However, it is also important to use the PAMI option tactically. Chi took his knowledge of parallel simplex to FICO, where the express simplex solver became the best in the world, and remained so for most of the time he was there. To summarize, there are many serial algorithmic and computational tricks, and many more than I have described. Exploiting parallelism can have a significant impact on performance for amenable problems. It's not the holy grail for overall benchmark results, but it may be valuable for a particular customer's class of problem. The ultimate performance gain comes from identifying and adapting the best combination of techniques to use at runtime. Here are references to the associated publications.